Okay, hi there, Dr. Matthew J. Trom here. Oh, there's my laser pointer. You. All right. So this is the last lecture of Module One. Uh, Module One, remember, is mostly conduction, um, and Lecture Five here is heat transfer from extended surfaces, also called fins. We're going to cover section 3.6 in the lecture. This is actually a really long section, so it warrants its own lecture all by itself. I would also like you please to read section 3.7. That covers things like thermoelectric generators, the bioheat equation. Sadly, we don't have enough time to talk about that in lecture, but those equations are becoming more and more prevalent and prominent in mechanical engineering, kind of real world industry problem solving, as mechanical engineers spread out into solid state materials and like biological solutions. So good for you guys to read that and just be aware that those equations and models exist. Um, as always, I'm recording this right now, so I don't have the link to the ADA compliant transcription, but once I'm done recording this, we'll have a Zoom transcription. So for those of you who need the transcription, I'm going to drop a link here, which you'll be able to access and get that transcription. Okay, let's see if we can change slides. Nope, my mouse is stuck. There we go. Okay, so by now I like to start my lectures with a meme or a cartoon, and this has nothing to do with heat transfer. Well, I guess it does a little bit, right? Because heat transfer is right here. But this came through my social media feed, and probably about this point in the class, you guys are starting to feel this way a little bit. So I thought this would be, just kind of um, a funny meme, right? So here we're just measuring with calculus and everything is fine, and then we get into linear algebra and we're cutting off thumbs and thermodynamics. We're smashing our fingers and heat transfer. We're basically cutting our hands open, and then fluids. Yeah. Anyway, you get the idea, right? So in the end, you have this, beautiful mechanical engineering cabinet with all of blood stains on it from all the various pain and suffering that you've experienced throughout your journey through mechanical engineering. So like I said, you're probably feeling a little bit of this summer because this class is a lot. So I thought this was just sort of a humorous way to point out that you guys are all working very hard, and I'm aware of that. So thank you for that, and hopefully we can all keep up with this breakneck pace that summer demands. Okay, so we talked quite a bit about conduction. And a big question that mechanical engineers who do thermal engineering have to face is, what happens if you just don't have enough surface area to get the heat out of the object that you are trying to keep cool, and thereby the object overheats. And so important one-dimensional heat transfer question is how do we increase the rate of heat transfer? And so, just as an example of this, um, I've got a CPU here, right? So CPU is like a central processing, just a chip that is the brains of a computer. And I say, consider a CPU just below the failure temperature, which is about to be overclocked, meaning it's basically running as hot as it can get before this happens, right? So I've got an image here of a chip where you can actually see the thermal damage and the melted solder, right? So this is a chip that exceeded its maximum temperature and very clearly failed and got damaged. So consider a CPU just below its failure temperature about to be overclocked, right? So you're basically putting as many calculations through the chip as you possibly can at this point. Any additional computations, any computational speed is going to dissipate more heat and cause you to basically exceed your failure temperature. And so, but right, I mean, you guys, I'm sure, have all played with overclocking your computers. Maybe not anymore. Maybe that's maybe a millennial thing. But anyway, um, You always want to ask the question when you're designing a computer or any sort of electronics device, how do you increase the heat removal rate? Um, without the thing overheating, right? And in this case, your goal is to enable faster computational speed. So how do you do that without overheating? Well, if you look at what's going on, right? So this surface here in schematic form is meant to represent this surface of the chip. You've got some sort of air, usually, driven by a fan, so forced convection, blowing over the surface. And so we're reliant upon Newton's law of cooling for forced convection. Q is equal to H A T surface minus T infinity to drive heat transfer away from the surface and keep the underlying chip cool. And so if you look at this equation, what dials do you have to turn? Q dot is increasing because you want to overclock the chip. T surface is limited because if you get too hot, the chip fries, right? So it's this temperature is limited by the temperature tolerance of the tip of the chip. So you've literally got three handles that you can turn. So one is H, right? So higher H means you have to increase a flow velocity, meaning a bigger fan, or maybe you switch from a gas to a liquid. There are liquid cooled computers now that the reason that they're liquid cooled is because you can get a much higher H and hence dissipate a lot more heat, so it can do more computations per time by overclocking the chip. But that's expensive and difficult to do, and sometimes you will reach a maximum capability for your fan or your pump, and you just can't get any more mass or volume flow rate over this surface. So this one is limited. Then the other possibility is increasing the difference between the surface temperature and the ambient temperature. That means lowering the ambient temperature, right? Which, okay, maybe you could do to some extent with air conditioning or something like that, or maybe using, like a pre-cooled gas and blowing a pre-cooled gas. I've always seen people kind of, like to play with liquid nitrogen, which is hilarious because liquid nitrogen has almost zero heat capacity. Um, so it, gets you colder, but it doesn't really help in terms of your ability to carry heat away. But anyway, this also becomes, there's sort of exotic solutions to get this temperature to go down, right? When you've got a perfectly good supply of 20 degrees Celsius or 293 Kelvin ambient air that you can just blow over your chip, right, without doing anything. And so really what it comes down to, more often than not, to get increased Q, is to increase the surface area. So this is often the most feasible way to increase Q is to attack A. So that's what this lecture is really going to be about. So the way that we attack A, increase A, is just basically by extending the surface. You can see here, this is just an array of fins, pin array, that's thermally pasted on top of a computer CPU, which of course you can't see because it's underneath. But all I'm doing with this is just extending the area available for heat transfer. And you can see schematically down here what I'm doing, right? I'm just taking that original flat surface and I'm just having these fins just come off of the surface. And in so doing, I'm just increasing the area in Newton's law of cooling that facilitates that convective heat transfer away from the surface. So just increasing A without, by the way, increasing the real estate that the underlying surface takes up, right? This sits right on top of the chip. So I'm not taking up any more space than the chip was originally intended to take. I'm just, growing vertically, right? Growing skyscrapers to increase my heat transfer. So these are called extended surfaces. And it turns out that extended surfaces or fins are an important special conductive 1D heat transfer case when you have convective boundary conditions. So all of the stuff that even though right, there's two dimensions here, right? You could still use all of the one-dimensional like resistor model and all that stuff that we talked about in previous lectures. So these are actually really powerful and really useful because you can use like all the stuff you already know from 1D and just extend it into two dimensions without actually having to solve a two-dimensional heat transfer problem. So I say here for extended surfaces, heat transfer from boundaries is perpendicular to the solid's principal heat transfer surface. or heat transfer direction. So all I mean there, right, is the principal heat transfer direction is here, and we're just growing these fins out of that surface and essentially opening up another like perpendicular surface, right? So like this surface that allows us to transfer more heat because we've just increased the area. So all these extended surfaces are called fins. And now here's the critical thing, which this took me a while when I was an undergrad. I did not appreciate this until I got into grad school. But once you see this, you can't unsee it. Like everything becomes a fin. And so you start seeing fins everywhere. So we've now received the presentation from Sandvik about their rotary blast hole drill rigs, right? So here's a drill rig, right? So all this heat is being generated by all the equipment on this surface. And look at this thing, right? Here's the mast that holds the drill bit, right? So the drill bit goes through here. And this mast is just a huge extended surface. And we actually talked about this in the context of thermal management. Could you actually, and this thing is made out of metal, right? So it's pretty conductive. Could you actually use the mast as a way of dissipating some of the heat from all these electromechanical components here on the base of the rig? So this is a fin, or at least it could be if it was utilized to that in that way. Another place where things that aren't supposed to be fins become fins, and this becomes problematic, is if you're using a thermocouple, or in our case, a thermistor, right? It still has wires coming off of it to measure temperatures. So this is actually quite problematic when you're trying to get an accurate temperature measurement because these things get welded to a surface, right? So you're interested in measuring the temperature at this surface, and yet here are these long spindly things, these little wires that come off of the thermocouple, and those start to act like fins, and they'll actually convect heat away and end up causing the temperature at this spot to be different than it would otherwise be if those wires weren't there, right? So this is actually a big problem in surface temperature measurement. People forget that the wires coming off of a welded thermocouple actually behave like fins and can mess up your temperature measurement, actually give you a false measurement. Made worse, by the way, since we've talked about critical radius now in the context of the quiz, made worse by the fact that these are usually pretty darn small wires, and a lot of times they'll be insulated for electrical isolation, electrical resistance, but because they're below the critical radius, the insulation actually makes them more thermally conductive, right? So you have these really thermally conductive insulated wires coming off of the spot that you're trying to measure the temperature of, and it actually will mess with the temperature of that spot. In this context, potentially fins are a good thing for heat dissipation. In this context, potentially they're a bad thing if your goal is to try to get an accurate temperature measurement, and you've got this fin effect kind of changing the temperature of the spot where you've got a fixed thermocouple. So anyway, the take-home message is that like I said, once you see this, you can't unsee it. You'll start to see fins everywhere. Sometimes they're intentional, sometimes they're not. But literally everything that protrudes from a surface behaves thermally as a fin. So kind of neat to think about. Okay, so there's all kinds of different fin types. So we have straight fins of uniform cross section, which is where we're going to focus because the math is relatively easy. We have straight fins of non-uniform cross section. So these normally take the shape of like triangles. We have annular fins, right? So when we were talking with Sandvik, actually, I'll talk about that down here. But annular fins are just, like a collar welded onto an internal conducting member. And then we have pin fins, right? So I kind of described. So I can go back, right? These are very pin-like, right? They are sort of isolated and they stick out from the surface. So isolated, stick out from the surface, sometimes conical, sometimes not. So a bunch of different geometries there. And then we have also different types of fin tubes. So when we were talking with Sandvik, we were talking about their oil cooler and the fact that you would run hot oil through, so see liquid flow, run hot oil through these hollow tubes, and then you would have some sort of collar like welded add-on annular fin on the outside of the tube, and then you with the fan, right? So remember they were talking about that big fan, blow air, force convected air over the fins, and exchange heat with the liquid that way, right? So that's a very common kind of heat exchanger type configuration. And then there's also compact heat exchanger configurations where you have hollow tubes that carry liquid, and you also just have a series of plates that connect them, right? So we'll talk more about kind of these configurations when we get into heat transfer. This is heat transfer. When we get into heat exchangers, there we go. But just to point out that there's all kinds of different configurations. So our overall goal in trying to analyze these fins is basically twofold. So first is we are interested in finding the temperature at any location along a fin, right? So if you start with the base temperature, you want to be able to basically traverse through the fin in this direction and find the temperature of the fin at any spot along the fin. So that's goal number one. And then goal number two, which is, really the main goal, is the whole purpose of sticking this fin on the surface to begin with was to enhance the heat transfer from the surface. And so you want to find that added heat transfer removal rate that the fins provide, right? And make sure that it's actually a good investment of resources to actually add those fins to your surfaces. There we go. Okay, so here's the kind of overarching general fin analysis. And so, like I've done before with these kind of differential analyses, I basically said, look, if you want the gory details of how this is done, it's in the book. Go check it out in the book. I'm just going to give you the end result and assume if you're interested that you can derive this by yourself because you've seen this kind of derivation in mechanics of materials and fluids and a bunch of other classes. So you guys can do this by now. So we're gonna take our fin and we're gonna slice it into infinitesimally thin sections of length dx, right? So here's the length dx, and then there's an underlying key assumption here. This is the fin assumption, which is the following, that each thin section's temperature is uniform across its width. So what does that mean? That means that from this spot all the way to the edge for this particular slice, the temperature is the same. There's no temperature gradient in the radial direction. It's all the same temperature. This entire slice is all at the same temperature. Now, most certainly, the fin is going to change temperature from the base to the tip, right? So you are going to have a temperature gradient in the x direction, x axis, but you are not going to have a temperature gradient in what I would call the radial direction, right? So that's an underlying assumption that must be true for this to work. The way that I've sort of illustrated that is here, right? So here is a situation for which fin analysis does not work, which is if you have a material that has relatively low thermal conductivity, high thermal resistance, and you have heat kind of propagating up from the bottom, and it generates this parabolic shaped temperature profile where the surface temperature is lower than the temperature at the center of the fin. And the surface temperature over here is lower than the temperature of the fin, internal temperature of the fin. That is a situation where you absolutely do not have uniform temperature across the width of the fin, and you cannot use the fin analysis to solve a problem that looks like this, right? So it has to be this, where you have a surface temperature on one side, a surface temperature on the other side, and you just have a flat temperature profile, same temperature all the way across, right? So I've got the X here, and I've got the check mark here because this is the temperature profile that we're looking for. So that is an underlying assumption that gets made when this equation is derived. So provided we have infinitesimally thin section of fin, and we have that each one of these little sections is uniform in temperature. You can perform an energy balance just like we did before with 1D conduction, and out pops this equation. Temperature is a function of x, so that's the temperature at any spot in the x direction. Remember, they're all uniform in r, but they're changing in x. T infinity is the ambient temperature, right? So that's the temperature out here of whatever gas is blowing over this fin. X is the coordinate down the fin's normal axis, so in this direction right here, right? So here's X. AC is the cross-sectional area. So you can see here in the schematic, AC is like this surface, so the surface of the slice of the fin. P is the perimeter, So the circumference all the way around this circle would be its perimeter. And then H is the convective heat transfer coefficient on the external surface of the fin, and K is the conductive heat transfer coefficient, um, basically thermal conductivity, right, on the inside of the fin. So, okay. So with that kind of as the grounding, um, we are going to make our lives easier using something called excess temperature. Excess temperature is really just, if you guys remember from fluids, those who took fluids with me, the law of conservation of chalk, which I often joked about. So back 1,000 years ago, when I was a freshman at my own undergrad alma mater, UC Irvine, I had a chemistry professor who'd always joke about the law of conservation of chalk, which was just things that scientists and engineers write in kind of, abbreviated form, so that they just don't have to write the same long equations over and over and over again. And this is just that, right? So we're gonna basically just define this thing called theta, and theta is the temperature difference between whatever the temperature happens to be at a particular X spot and the ambient temperature. And so the key thing is if we take a spatial derivative of theta with respect to X, which is this d theta, we get the derivative of these temperatures that are on the inside. This one is a function of X. This one is a constant. And so we just end up with the derivative of the temperature in the X direction, right? So that's going to come in handy because we got a lot of derivatives in this equation. So um, d theta is essentially just dt. Okay, so in the situation where we have fins of uniform cross-sectional area, um, in the fin equation, there's this middle term here. Let's go back. There's this middle term here. This is, you guys recognize this, right? That's the conductive heat flux. This is a term that gets multiplied by the first derivative of temperature and accounts for the change in the cross-sectional area as a function of x. And then we have this term, which is, basically the convective term. So if we are in a situation where we have uniform cross-sectional area, this dAc dx is zero because we are not changing the cross-sectional area as we march forward down the pin in x. So that term goes away, and this first spatial temperature derivative goes away. And so we're basically left with this guy. So d squared t over dx squared minus hp over kac times t minus t infinity. We're going to use our t minus t infinity as theta, and that our derivative of t minus t infinity is d theta. And we're also going to use this definition for lowercase m. So m squared is equal to HP over KAC. And this always kind of weirded me out. It's like, why square it? Like, that's a very weird, like, why do that? And you'll see, right? So when this thing gets solved, it turns out that the solution to this equation has basically the square root of this thing in it. And so it's much more convenient to just square m to begin with, and then end up with m just all by itself without the square when you get to the solution, right? So that's just like just people not wanting to write the square root sign over and over and over again by just naming this variable and then squaring it. So, okay, so we take kind of those conservation of chalk type principles and we plug them into this simplified version of the equation. And we get d squared theta dx squared minus m squared theta. Yeah, m squared theta equals zero. And this is an equation that has solutions of this form, differential equation that has solutions of this form. I should mention second order differential equation, right, that has solutions of this form. And so what that means is we need two boundary conditions. One is pretty obvious, which is that the base of the fin at x equals zero, right? This is the x direction. So the base of the fin at x equals zero is the temperature of the slab that the fin is attached to. So that's this boundary condition, which is given. The other boundary condition, it turns out there's multiple different possibilities that give multiple different answers. So we'll talk about that on the next slide. But we have one boundary condition. Notice that if you're a fan of hyperbolic sine and hyperbolic cosine, there's two different ways to write this, and it sort of depends on like, what's the most convenient. So there's this form of it, which is that theta of x equals some constant of integration times e to the mx minus some other constant of integration times e to the minus mx. That's one correct form of it. Another correct form is just that same theta is equal to constant of integration times hyperbolic cosine of mx plus some other constant of integration times hyperbolic sine of mx, right? So these two equations are equivalent. One is just in terms of the natural number, and the other one is in terms of hyperbolic sine, hyperbolic cosine. So, okay, so we've got these solutions, and now we have to deal with that second boundary condition. So it turns out that there are four very common boundary conditions that appear a lot in heat transfer. So one is, and so we're talking about the tip of the fin, right? So what happens along this surface if we've got a rectangular fin, or along this surface if we have a circular fin. And so these are the four possibilities. So one is that we just have convection at that spot, right? And so we've seen this before. This is an energy balance from conduction in a solid to convection in a fluid, right? So the heat transfer from the solid to the fluid has to follow the first law of thermodynamics. So that's what one possible boundary condition at x equals L, the tip of the fin. Second possible boundary condition is adiabatic, meaning no heat transfer at all from the tip. In that case, we know from previous discussions of adiabatic boundary conditions that the derivative of temperature at the tip with respect to x has to be zero, right? And if it's zero, there's no heat transfer, so hence adiabatic. So that's another boundary condition that we can put in. A third possible boundary condition is a prescribed temperature. So somebody comes along and tells us, okay, the temperature at the tip is some value, right? So that's this getting prescribed. And then there's the fourth one, which is a little bit weird. We're going to talk about this in more detail a little bit later in an example. But it's this idea of an infinite fin, right? So the fin is like infinitely long. And because the fin is infinitely long, eventually it will reach the same temperature as whatever the ambient temperature is. And so theta at some length, which is infinitely far away from the root, is zero because you don't have any more temperature gradient at some point. So we're going to talk about that one a little bit more because that one's a little weird. Okay, so for these four conditions, we have four different possible temperature distributions, which are given here in these equations, and four different possible heat rates. So this is the heat transfer from the base where the fin is attached up through the fin and out into the ambient environment, right? And remember, if we go back, these are our goals, right? Is temperature at any location along the fin and added heat removal rate the fin provides. So these equations give us precisely those goals, right? So great. As a quick note, two quick notes. So more, kind of law of conservation of chalk. We talked about lowercase m, which is here. There's also, I don't know why they do this. The notation is really bad, but also uppercase m, which is here. And uppercase m is not lowercase m, right? So uppercase m is the temperature difference at the base. So this is TB minus T infinity multiplied by the square root of HPKAC. Convective coefficient, perimeter, thermal conductivity, and cross-sectional area. So I say here, note number two, capital M is not equal to lowercase m. This is a very common mistake because it's really easy when you write, problem solutions by hand to get these mixed up, right? Because capital M, lowercase m, they look very similar. right? Especially if you're doing it by hand. So just be aware that these are two different M values that have two, and more confusing, right? They have all the same variables in them for the most part, right? They're just organized in a different way. So just be careful not to mix capital M and lowercase m. I really hate the notation, but this is the notation that's been used for years, and the notation that's in the book. So we really can't fight it. It's basically set in stone now. Okay, I will mention here, this is, 2026. You guys have the power of AI. And so it would be interesting, I think, for you to explore other possible tip conditions. And you can ask AI, like, what are those other possible tip conditions? And what is the resulting temperature distribution and um, heat transfer rate into the fin if you had, for example, something like a contact resistance at the tip of the fin. We talked about contact resistance in a previous lecture. Or if you had a situation where you have both radiation and convection at the tip of the fin, or some other boundary condition. And it used to be really hard. You'll see because we're actually going to go through one of these derivations. Really hard to get these expressions. It was a lot of work. But now you guys have AI. All the work gets done by a computer. So I could, for example, on a quiz, ask you to solve for a situation which is not one of these four cases and figure out the temperature distribution equation and the heat transfer rate for some, arbitrary fifth case, sixth case, seventh case, provided I give you what's happening at the tip. You should, with the assistance of AI, be able to come up with the correct version of the temperature equation or the heat transfer rate equation for basically any boundary condition that I give you, right? Not necessarily these four, but anything that I give you, you should be able to figure out what the appropriate temperature and heat equation are for those. So I just want to mention that so that you're not surprised if you see that on a quiz. Okay, next slide. So I want to go through, and I just mentioned that these are, kind of massive pains in the butt if you do this, step by step manually. But I did want to go through and just show you where these equations come from for basically the simplest kind of sensible condition, right? Which is an adiabatic tip. So this is a situation you have no heat transfer off of the tip of the fin. It's either insulated or some other way that there's no heat transfer there. Um, Even simpler solutions do come from the infinite fin, but I don't think we really have our heads wrapped around what an infinite fin is yet. So I didn't want to do this one until we had an example where we could talk about it. So I'm going to do the second most difficult one, which is the adiabatic fin. And I think I mentioned up here, yeah, the textbook shows the derivation for case one, which is the convection at the tip. So this one is actually done for you in the book, so you can see how that one's done. So I'm just going to do this one for you. Okay. So we're gonna do case B, which is an adiabatic tip. It's the same, just sort of square fin that we talked about before in Euclidean XYZ geometry. And all that has happened here is I've just put some piece of insulation on the tip of the fin to ensure that the derivative of the temperature difference with respect to x at x equals L, right, which is this location, right? Here's x, here's L, right there, is equal to zero, adiabatic, right? So usually just done by putting a piece of foam or something on the tip. Okay, so that's our second boundary condition. We have our first boundary condition from before, which is the temperature at the base is the temperature of the underlying surface. That's this one. And then here's our second boundary condition. So now we can take this differential equation, second order differential equation, two boundary conditions. We can solve it. Because I know where I'm going, I know what the answer is. I'm cheating here a little bit. I'm going to choose the hyperbolic cosine and hyperbolic sine version of the solution. You can also, of course, do this with the natural number. It just the math is just more complicated, but you end up getting the same result either way. So I'm going to go with this. Um, and then I'm going to take the derivative of it, right? So if you remember taking derivatives of hyperbolic sine and hyperbolic cosine, what's on the inside, if it's a function of x, comes out, right, as a derivative. So the first derivative of theta with respect to x is just mc1 hyperbolic sine, right? Cosine goes to sine, mx plus mc2 hyperbolic cosine, sine goes to cosine, mx. And now I'm going to plug in my boundary conditions. So if I put in boundary condition number one, I'm plugging that into this original version of the equation. At the base, the temperature is the temperature of the base. So I'm taking a hyperbolic cosine of zero, basically hyperbolic sine of zero. And what falls, and that all equals theta b. And so what falls out is that hyperbolic cosine of zero is one, hyperbolic sine of zero is zero. So I'm left with C1 is equal to theta b. And so that gives me my first constant from that first boundary condition. So now I can take this and I can plug it back into the equation. And now I'm going to take the derivative version of this equation and I'm going to apply the boundary condition two for the adiabatic tip. So here I'm doing that, right? So here's the first derivative. So I'm plugging in my C1 and I'm plugging in the fact that I am now at L, right? The full length of the fin. So that's where this ML comes from, ML. And what pops out of this is that C2 is equal to minus theta b hyperbolic tangent of ML, right? So now I've got C1, I've got C2. I could take those and I can plug them back into my equation. And so I get this guy down here, right? So that's basically the solution to this differential equation given that I know the temperature at this spot and I know that this spot is adiabatic. Okay, so now that I've got that, I'm going to just use some clever trigonometric or hyperbolic trigonometric identities. I don't go through it because it's like a slide would be required to show the derivation, but just trust you could look it up that this combination it ends up equaling this combination. So hyperbolic cosine of ml minus x over hyperbolic cosine of ml. And so that equals, right? I pull theta b out from both of these terms because it's the same theta b coefficient. I just divide both sides by theta b. And so I end up with this ratio of theta at any x to theta b is equal to hyperbolic cosine m quantity L minus x all over hyperbolic cosine of ml. And I checked in the book and AI agree with me, so I get the green check mark. So yay, good for me. Okay, so I've got the temperature distribution. Now I need to find the heat flux from the base because that's the whole point of putting a fin on the base to begin with, right? So what's the heat flux out of that surface? The heat flux out of the fin has to be the heat flux into that surface. So I'm going to say, okay, we're going to take Q dot fin. This is, of course, Fourier's law for conduction. Um, so I'm just basically figuring out what the conduction is from the base into the fin. So that's this. I know this theta equation because, hey, there it is, right? So I'm going to take the first derivative of this theta equation with respect to x. That's this guy, right? So cos ml is a constant. Derivative of hyperbolic cosine is hyperbolic sine. The m comes out. Everything in the inside that's a constant stays on the inside. This negative sign comes out because of the chain rule, right? I've got a negative sign here that has to come out, right? So that's where that comes from. And now I've got my expression for heat flux at x equals zero, so heat flux at the base. And it's just this. So K times A sub C, that cross-sectional area, times theta B, the temperature difference, times lowercase m, times hyperbolic tangent of ml, right? So, and I know that this combination of variables, K, A, theta, M, starts to look a little bit like capital M. And so I'm just going to go through here and do some algebra, boop. And what comes out is just capital M, right? So this whole thing turns out to just be capital M. So I get Q dot fin is equal to capital M times tan H, hyperbolic tangent times ML. And let's just see, right? So I give myself a green check mark, which means both the book and AI agree with me here. And right, capital M, tan HML. The old guys still got it. I can still do math. Cool. Okay. So, so I've done it now. So you should be able to see in the book for case A. I've done it for case B. Case C is pretty easy, right? Oh no, I lied. Case C is actually the hardest one. You get all these ugly sines and cosines, hyperbolic sines and cosines. What I was wanting to say is case D is easy, right? You get these really nice, clean expressions, but you have to know what an infinite fin is, and we're not, we're not, ready for that yet. So you guys probably as an exercise should go through either case C or case D and just prove to yourselves that you can do this. Let AI help you if you want, but make sure that you can do this yourself and you can actually think through the process. Because again, right, I might end up on a quiz putting a case that's not one of these four cases and asking you to figure out what the temperature distribution and the heat transfer rate is. So you should be able to do it for these four cases so that you have practice for some arbitrary fifth case that I come up with. Okay, so now that we've basically got this table, right, that shows the temperature gradient and the heat flux for all of our different cases. We know how to get these expressions. Now we want to, do something useful with it. And so we're going to come up with a couple of fin performance parameters. So I say here, the goal of fins, of course, is to enhance the heat transfer from a surface by increasing the effective surface area. Fins are not a panacea, right? You can't just like slap any random fin onto a surface and just trust that it's going to give you enhanced heat transfer. You do have to actually design them very intentionally to function the way that you want them to, because the fin imposes its own conduction resistance, right? All of a sudden, there's this whole big, like chunk of metal that's sitting between the ability of the surface to just convect heat away, and the surrounding environment, right? So you're not guaranteed by just slapping a fin on a surface that it's actually going to do anything for you. It could actually hinder your heat transfer if you've designed it badly. I don't want to say anything bad about electrical engineers or computer engineers, but I used to teach back in Wisconsin the heat transfer class for the electrical and computer engineering department. It was a service class that our department taught for them. And you could always, I hate to say this, you could always tell who the computer and the electrical engineering students were because they knew, right, that they needed to put fins on their CPUs, right? This is a very common thing, but they would always design them in these sort of cockamamie ways where the fins were actually hurting rather than helping the heat transfer. They didn't actually know how to design them. They just knew that they needed, fins. And so they would design these things that weren't actually super helpful. So it is important to come up with some performance parameters to know that what you've designed, or to guide your design process so that your fin is helping and not hurting. So I say here, fins impose their own conduction resistance. You must confirm that adding a fin is beneficial before you add it, right? So this is an important step. Okay, so the first one of these parameters is called fin effectiveness, epsilon sub f, for surface at constant base temperature. The ratio of the fin heat transfer rate to, let's see, what is this? Ratio of fin heat transfer rate to heat transfer rate with, oh yeah, okay. So this is just a ratio, right? It's, think of it like an efficiency in a way. Um, so this is the rate of heat flux across this surface enabled by the fin. So Q dot sub F for fin. And then this is the rate of heat transfer across this surface if the fin weren't there at all, right? So that makes sense, right? H times ACB. AC, remember, is cross-sectional area and B is base. So this is just the area of the base without the fin there. And then this is the temperature difference between the temperature of the base and the temperature of the surrounding environment, right? So this actually makes a lot of sense. It's like an efficiency in a way. This is in the denominator, the heat flux that you would get if no fin was there. And then in the numerator, that's the heat flux that you get if the fin is there. Now, this heat flux that you get if the fin is there, of course, depends on which one of your boundary conditions you're dealing with. So I'm just going to take the simplest one. I think I did. Yeah, simplest one, which is the infinitely long fin. Ooh, and that allows me to talk to you about what an infinitely long fin actually means now. So just, moving forward for your edification, just note that I am taking Q dot F is equal to capital M. Why? Because, whoops, too far. Because, right, there it is, right? Infinitely long fin, capital M, heat flux rate. So that's where that comes from. And, too far. And if I plug it in here and M has got all these little variables in it, right? And so basically cancel out all the variables. What I'm left with is the effectiveness of this particular fin, this infinitely long fin, is the square root of KP over HAC, right? So, but this is not true for every single different type of fin. This is only true for an infinite fin. You'll have to do your own derivation of this for the three other cases, which is not hard to do. It's just, you have to do it. Now, what in the heck is an infinite fin, right? What is this infinite fin that you speak of, Dr. Traum? So, I kind of alluded to this before, but think about what happens if you have a really long fin protruding from a base, right? I've tried to represent it here with, kind of this color-coded temperature profile so that you can see what's going on. The base is hot, the ambient environment is cold, right? Basically, the blue temperature, that cold air is blowing over this fin. The fin is rejecting heat to the environment at whatever that temperature is. And you can see there is actually a temperature gradient in the fin where the fin itself goes from very hot at the base to, relatively cold at the tip. There is some length of this fin, right? It's right about here, probably. Some length of this fin where the fin's temperature has reached the temperature of the ambient environment, in which case there's no more temperature gradient between the fin and the environment. And so there's no more heat transfer between the fin and the ambient environment. And so all of the length of the fin that is past this spot where those two temperatures are equal is basically useless, right? It's kind of like a dead fin. But if you go back to, right, like the original equations, where are they? Oh yeah, here we go. Right, the original equations, right, and I'm I'm like plugging in, right. Look at these monsters. I'm plugging in like boundary conditions, right? It's much easier instead of saying, yeah, I'm not really sure like what the L is for the point where the fin is long enough that the temperature has reached the ambient temperature. I'm gonna have to, guess or hand wave or come up with something that's different for every geometry. It's just easier to say, well, hell, I'm just gonna put in, infinity here, right? And if I put in infinity here, like this thing just gets tiny, right? So that's why we do it. It's using infinity as kind of a stand-in for the length of the fin at which the temperature is no longer any hotter than the ambient environment. So that's what I mean by infinite fin. Infinite fin is a fin that's long enough that the fin temperature reaches T infinity, the ambient temperature, before it, that temperature profile reaches the tip. That's what it means. So hey, now you know, right? So now that you know what an infinite fin is, you can go back and do all these, right? Actually derive these for yourself, knowing what an infinite, right? You're just putting infinity in for L. And of course, this is that statement where the temperature difference at L, which is infinitely far away, is equal to zero, right? The tip of the fin is basically the ambient temperature. Okay, so we now know what an infinite fin is. We have an expression for effectiveness. I'm going to just use this version of the effectiveness expression for an infinite fin kind of as a stand-in for all of them. But there are some key observations that you can take away from just kind of, looking at this combination of variables. So the first one is that use of a fin is rarely justified unless the effectiveness is at least greater than or equal to 2, right? And why is that? Okay, fine. You're getting twice the heat transfer rate out of this small surface than you would if the fin was there. But right, you have to like go through all the trouble of manufacturing the fin, and this is now a surface that you can't just machine clean because you've got this stupid fin sticking out of it. And so like it actually is not really good from a manufacturing perspective to put fins on a surface unless you really need them for heat management. And so usually engineers will not put a fin on a surface unless the effectiveness is greater than 2. So that's the first point. Second point is effectiveness is enhanced with high thermal conductivity. So sometimes the fin and the base are two different materials, with the fin being a much more thermally conductive material. And you can see the benefit of that, right? If I've got a high thermal conductivity material like copper that my fin is made out of, and I attach that to a copper bearing, material like say brass or bronze, you can braze it on there. The high thermal conductivity fin helps my effectiveness, right? So it's always good if you can, if you're putting fins on anyway, to make them out of a material that's as conductive as possible. The effectiveness is also enhanced by increasing the ratio of perimeter to cross-sectional area. And so you can see here, right, P over AC. If that ratio goes up, then effectiveness goes up. And so what that means is you benefit from thin and closely spaced fins to a point. And there's actually an example where I'll solve this for you. It's actually fascinating. You can reach a point where the fins are so closely spaced to each other that you're actually messing with the forced convective heat transfer coefficient on the individual fins because the fins are literally sitting in each other's wake or sitting in each other's boundary layers. And so the effective H is actually reduced, right? We just did this in quiz one, right? Where the battery was sitting in the boundary layer of that thermal mat that it was sitting on, and H got reduced as a result. You guys know, you all did quiz one. So you can put the fins so close to each other that they will actually interfere with each other's forced convection coefficient. So this works to a point until you start messing with the flow field. Um, so okay, so what's this point? Find better justified when H is small. Oh, this should say fin. Fin, better justified when H is small. And so more need for fins when fluid is gas rather than liquid, right? So I'll fix it. That's a typo. So you can see here, right? When H is small, effectiveness is big. And so in a world where you're dealing with like, natural convection, or if you've got forced convection, but you've got kind of a really wimpy low velocity fan or something like that, um, it's actually better to use fins because the effectiveness goes up in those situations. It's also typically better to use fins with a gas rather than a liquid, right? Because in general, gases have lower H values than liquids do when you're in a convective situation. And so that leads us to the next one, which is if fins are used on surfaces separating a gas and a liquid, they're generally placed on the gas side, right? So how cool is this, right? If we go back here, this is actually good for your Sandvik project, right? If you go back here, look at this, right? So we have liquid flowing through the center of these tubes, no fins there, right? Because it's liquid, has relatively high H. And then we have gas blowing over the fins in this direction, and that's the surface that gets augmented and extended by the fins because gas has a lower H value than the liquid does, right? So fins usually appear on the gas side of a heat exchanger and not the liquid side of a heat exchanger. And now you know why, right? How cool is that? Um, right? It all just comes from effectiveness. Okay. And then I say here 99% of maximum possible fin heat transfer rate is achieved for the product of ml equals 2.65. So it's typically useless to extend fins beyond a length of 2.65 divided by m, right? This goes back to this idea of an infinite fin. Usually beyond L equal to 2.65 divided by m, 99% of the heat flux benefit that you would have gotten has now been used up. Your fin is almost at the ambient temperature, and you get very little additional heat transfer out of it. And so this is a good rule of thumb for fin design, right? Just don't make your fins any longer than this because there's no point in adding any material after that length. Okay. What's next? Okay. So, fin performance parameters, resistance. So we spent an entire lecture talking about the equivalent thermal resistance for 1D conduction, right? We talked about like composite walls, and we talked about porous materials, and we talked about what happens if you have like layers of different composite materials on top of each other and all that stuff. And all of that boiled down to the fact that you could come up with an equivalent resistance, and that equivalent resistance for your composite wall gets, you can use all of your skills for resistances in series and resistances in parallel from your circuits class. So wouldn't it be super convenient to be able to represent the heat transfer from a fin using an equivalent resistance? Why, yes, it would. So here we go, right? We actually can come up with the equivalent resistance. I think this is RT, either for sometimes T in the book stands for thermal and sometimes it stands for total. I'm pretty sure here it's thermal. So R thermal fin is just equal to the temperature difference between the base of the fin and the free stream temperature of the fluid blowing over the surface, and then the heat transfer that the fin facilitates, right? So it has the exact same form as a thermal resistance that we've seen before. And we can use, I'll show you later, we can use this in our 1D resistance equations when we have a fin present to basically represent the resistance presented by the fin as it's transferring heat away from a surface, right? So good to have this in our arsenal. We're then going to combine this idea of the thermal resistance associated with the fin with convection um, to come up with an equivalent um, convective thermal resistance at the base, right? So what the hell is this? This is 1 over HACB. So what do I mean by that? If we go back to, let's go back here, right? If I've got no fin on a surface versus whether I have a fin, when I do have a fin on a surface, the resistance presented by the area where the fin would be if I added it is HAC sub B, right? A sub C is the cross-sectional area of the fin, right? That's the area of the fin that gets stuck onto that surface. And then B is the base, right? And then this is the convection coefficient. So I can write this like resistance for that little section of the surface before I stick the fin on it. And now you could kind of think of effectiveness in a different way. Effectiveness can also be written as a ratio of the resistance in the numerator of the fin divided by the resistance in the denominator of that little section where the fin is attached to, right? And if you actually plug in the numbers, you get this the exact same expression that we had before, right? Exact same expression for fin effectiveness, right? So that's why I've got my little exploding brain here, right? Is I think that's just a very cool way of thinking about it. It's just a ratio of resistances, the resistance that the fin presents in the numerator and the resistance that the little section of the surface that's getting cooled presents in the denominator, right? Just a neat way of thinking about it, I think. So I say here, it reveals effectiveness as a ratio of thermal resistances. If the fin is to enhance heat transfer, the fin resistance must not exceed that of the exposed base, right? So, right, obviously. So if you take this ratio and you end up with a value less than one, right, the fin is not helping you, right? It's actually hurting you because it's impeding heat transfer out of a surface that otherwise would have been free to convect heat away, right? So you definitely want this number to be bigger than one. And like I said, it's usually kind of a rule of thumb that we only will put a fin in place if that number is greater than two, greater than equal than two. Okay. Um, all right, so let's talk about another fin performance parameter. This one is the fin efficiency. This one is like a true efficiency, whereas the effectiveness was kind of a more like a COP actually. So this one is a true efficiency. So I say here, another fin performance measure is fin efficiency sub fin, defined by the actual fin heat transfer divided by the maximum possible heat transfer rate. Okay, what in the heck is the maximum possible heat transfer rate? Well, I say here, maximum possible heat transfer rate from the fin would occur if somehow magically you are able to keep the fin all the way down its length, all the way from the base to the tip at whatever the base temperature was, right? This is hypothetical. This isn't going to happen in the real world because, of course, you're gonna lose temperature as you move down the x-axis of the fin away from the heated base. But just imagine that you had some way of keeping the temperature of the fin at the base temperature all the way down the length of the fin, right? That's the maximum possible heat transfer that you could get from extending the surface out from the original surface from which you're conducting heat, right? So maximum heat transfer rate from the fin would occur if it were entirely at the base temperature TB. So what you end up with is this ratio of the actual heat transfer from the fin divided by the maximum possible heat transfer from the fin, and you end up bounding this so-called fin efficiency, which is that ratio, by zero, right? That's zero is if you just have like an adiabatic like insulator that you just stick on here, right? The fin is just a big chunk of styrofoam that's not helping you at all. That's zero. Or one is the magical situation where you actually do somehow manage to get, you know, constant temperature all the way down the fin, right? So 0 and 1, those are the bounds of efficiency. So this one does actually behave exactly like efficiency. That's why it's called efficiency. Okay, so for a straight fin of uniform cross section and adiabatic tip, right? So this is a specific situation. And I'll talk about this, even though it's a specific situation, sort of in general terms. And I'll leave it to you guys to either look up, have AI derive for you, or derive for yourself the equivalent fin efficiencies and resistances associated with those other configurations. Um, so it's just q dot fin divided by q dot max, right? So q dot fin just propagates through, and then q dot max is just HAF times the temperature difference. But this is the temperature difference where T base is the temperature all the way down the fin, and then T infinity is the ambient temperature. So that's, of course, just theta B. Um, and we have this new thing called AF, right? Before we were talking about AC. AC, just to remind us, AC is the cross-sectional area of the fin. A sub F is, I say it here, AF is the fin surface area, right? So the surface area of the fin. It's kind of like the perimeter of the fin multiplied by the length of the fin, right? Is the um, A sub F. Okay, so the fin resistance from the previous slide can also be written in terms of fin efficiencies, right? So you can imagine how this could actually start to become useful. We like to have resistances so that we can make those nice one-dimensional thermal circuits that are so easy to solve to model heat transfer situations. And we can use this definition of fin efficiency, which is pretty simple, combine those ideas together, and you end up with the fact that R resistance thermal of the fin is just equal to 1 over H area of the fin times the efficiency of the fin, right? So if you need this R value, you can just get it from the H, the area of the fin, and then the efficiency of the fin, which can be calculated as shown up here. Um, okay. Okay. So this is just me saying, okay, look. This is the generic version of the equation. I'm now going to take a specific case, which is my friend, the adiabatic tip, and I'm going to put in the Q value, Q dot value for adiabatic tip into my efficiency equation, and out pops an actual expression where you can plug in things like an M value and an L value to actually get what the fin efficiency is, right? To then plug into here to again, then a resistance to then put into your one-dimensional heat transfer model. Um, so where does this come from, right? We've already derived it, but just to remind you, right? Adiabatic tip, here's the Q value, so that's where it comes from. And I'm just plugging it in, and I'm recognizing that all these little variables down here, the H's and the A's and the thetas, all look an awful lot like M. And so I'm just like canceling things, and I end up with hyperbolic tan of ml divided by ml is the fin efficiency for a fin with an adiabatic tip, right? It'll be different for other boundary conditions, but for an adiabatic tip, this is what it is. For the other ones, you guys can look them up, aha, or there's a table. There's a table. Uh, Maybe not for all situations. So you can either look them up or, AI can help you. Okay. All right. So ready to transition now to something a little bit more complicated. Um, we're going to talk about fins with non-uniform cross-sectional area. So we're going to go all the way back to our original fin equation, right? Remember, this got derived from the energy balance on just the differential section of fin. And what we were able to do before is say, look, the cross-sectional area doesn't change with respect to X, so we're going to cross this term out, and we get all those nice solutions that have those hyperbolic sine and hyperbolic cosine in them, and those we can manage relatively easily. But oh man, in a case where the fin is actually tapering down, right, it doesn't have constant cross-sectional area, the derivative of cross-sectional area with respect to x is not zero, and so this term has to be retained. And oh man, the math gets a whole hell of a lot worse in that situation. So I say here, the second term of the fin equation is retained for fins of non-uniform cross-sectional area. Solutions are no longer in the form of simple exponential and hyperbolic functions. Oh lordy, just use tables, right? So maybe AI can help you with this, but back in the day when I was young, we used to walk uphill in the snow both ways to school. There were tables for that, right? So AI is helpful for you now, but know that there are tables that can back you up if you find yourself on a desert island without a cell phone or cell service or access to an AI. So here's three conventional kind of straight fin examples. So this is the one that we've already talked about. This one does, of course, have a constant cross-sectional area. So this one we can solve fin efficiency for, right here it was on the previous slide. Fin efficiency for just using our simple exponential and hyperbolic functions. Here's a triangular fin, right? So we can get the expression for it from here. Here's a fin that has like a parabolic cross section, and we can get the expression for it from here. Um, why, by the way, would you want a triangular fin or a parabolic fin? Well, sometimes you're doing things like trying to reduce the amount of material that you're using or trying to reduce the weight. And so these shapes will give you very similar heat transfer performance to this shape, except they weigh less and they use less material, right? So they're beneficial in that regard. Okay. Um, Next, we want to go to some more non-uniform cross-sectional fins. Let's talk about annular fins. So here is an annular fin. What is an annular fin? Well, this is just like the tube and collar fins that we talked about before, like for the Sandvik situation. So I have a hollow tube that has gas running through it, and then that hollow tube has some sort of metal collar on it, and that metal collar provides the extra area for the enhanced heat transfer. So you kind of see it here in cross section. Right here's the center line. Here's the hollow portion of the tube. Here's the solid portion of the tube, and then here's the collar that gets attached to the tube and the relevant dimensions. Oh dear Lord. Here's the efficiency, and it has all these weird variables, right? Like, what is this? K1, I1, I1, K1. It's like a game of bingo, right? What in the heck are these things? So it turns out, right, and I've got my little scared emoji here because, like, what are these things? It turns out that these things are Bessel functions, and I am not sure that you have ever seen a Bessel function before. Maybe you have in like a numerical methods class or something like that. But in case you haven't, there's a solution for this, and let me just walk you through it quickly. So where do we get these Bessel functions from? Like, where do they emerge from? Well, it turns out this thing is cylindrical, so we're going to use polar geometry. And so we're going to take our trusty fin equation, which we derived in Euclidean geometry, and we're going to turn it into polar coordinates, which I do here. And so this term has this 1 over r in it that I like so much in the rotational polar coordinate system. And we're going to solve this. We're going to solve it using kind of the same law of conservation of chalk tricks that we're using before, except now m squared is going to be 2h over kt times theta. And theta is that same old law of conservation of chalk, just the temperature at some radial location minus T infinity. And if we take those and plug them in here to just make this equation more compact, we get this version of it. And then here it is. And now we want to solve this thing, and we're going to solve it, and it comes out like this. So this has solutions of the following form. So theta r is equal to some constant of integration times I naught mr plus some constant of integration k naught mr. I want to clarify that these are functions, right? So they're just like hyperbolic sine, hyperbolic cosine, in that this is not multiplication. I'm not multiplying I by MR. I'm not multiplying K by MR. I'm taking a value of MR and I'm plugging it into a Bessel function, I or K, and out pops a number, the same way that sine and cosine work, right? So just want to be really clear about that because that was really confusing to me when I was an undergrad. I probably got, my final exam, questions wrong because the professor put something like this on there and I multiplied MR by I and got it wrong. So not multiplication. These are functions. Um, okay. And what functions are they? Well, they are so-called modified zero order Bessel functions of the first and second kinds. What that means is not important. What is important is that the solutions are tabulated. Bessel function numerical values for a range of possible inputs are listed in the textbook in table B5, which I copy and pasted here for you. Now, in 2026, right, in a world of AI, I checked. AI knows what a Bessel function is. You could say, hey, bro, AI, bro, like, I want the modified zero order Bessel function of this, and it'll be like, I know what that is, and it'll just pop it out, right? But back in my day, again, when we walked uphill in the snow both ways to school, we didn't have AI and we had tables, right? So I do want to show you that this technique is here, that this technique gets used, just in case you don't have access to AI or you come into it, you should always check, right? I've kind of emphasized this in this class a whole bunch, right? Do not trust the AI. Always make sure that you're doing your own separate hand calculations using the old methods to make sure that the answer that the AI is giving you is correct. Do not just blindly trust it. So I'm going to show you this technique so that you can use it to check your AI solutions. So let's just do just a really quick example. This isn't even a heat transfer example. This is just how to use the Bessel function table to get an answer. So let's say that my MR value sitting inside this Bessel function, I0, so I'm looking at I0 of MR, is 1, right? So MR is 1. And I'm told to find the value of the Bessel function for MR equals 1. Okay, fine. I'm going to go to my table. In this case, MR is just X, right? So I'm looking across here at these guys. This is e to the minus X, I naught X. This is e to the minus X, I sub 1X, e to the X, K naught X. Okay, so it's definitely this one, right? So I naught X, I naught MR. In this case, X is MR. So MR is 1. So X is 1. So I go down the table and then I read across until I get to this value. So this is not the value of the Bessel function. This is the value of e to the minus X times the Bessel function. So I have to get the Bessel function all by itself. So here I am doing that. So at X equals 1, this e to the minus X Ix is equal to 0.4657, 0.4657. That's where that comes from. And I'm going to plug in X equals 1. So I get e to the minus 1, right? Because it was X, now it's 1, multiplied by the Bessel function at 1 is equal to 0.4657. And now I'm going to multiply both sides by e to the 1, and it gets canceled over here. It just becomes 1, and then it appears on the other side. E to the 1 is approximately 2.718. If you're like, a super savant, you know it to more decimal places. I don't need it to that many decimal places for this example. And so I'm just going to multiply that 2.718 by my original tabulated value, and out pops 1.266, right? So this is the actual value of the zero to Bessel function of the first kind for MR is equal to 1. It's 1.266. Okay, so hopefully if you ever have to solve an equation like this, now you know how to use this table to validate what the AI is doing, make sure it's right. Okay, cool. Let's move on. All right. So this is just another table to show that we have pin fins, right? So another non-uniform cross section. Here's the uniform cross section pin fin that we talked about before. And then here is a triangular fin that's a pin. Here's a parabolic fin that's a pin. And these are the associated fin efficiencies for those. So again, use a table. But notice, right? These are Bessel functions, I sub 2, I sub 1. So this one has Bessel functions in it. Um, this one has Bessel functions in it. Even back here, oh, I went too far. Yeah, this one has Bessel functions in it. This one has Bessel functions in it. This one has Bessel functions in it. So you are going to have to manage Bessel functions if you're solving these things by hand or validating the AI. Okay, so next let's talk about overall surface efficiency. So we talked about the efficiency of an individual fin. Now we want to extend, right? So I say here, N sub F characterizes single fin performance. I want to extend that analysis to an array of fins because, right, wouldn't it be convenient to just be able to create an array of fins that are all identical and say, look, this array of fins has some efficiency associated with it, and hey, maybe even also a resistance, like the way that I did with a single fin before. So we're going to come up with a ratio, which is overall surface efficiency that characterizes an array of fins and their base attachment surface as opposed to just a single fin. And what is that? Well, it's just the heat transfer from all of those fins divided by the maximum possible heat transfer again if all of those fins were maintained at constant temperature of the base all the way down their length, right? This is just this concept all over again, right? Same temperature all the way down, except now for an array of fins instead of a single fin. Oh, too far. Okay. Um, so I say here Q sub T is the total heat rate from the uh, surface area A sub T associated with the fins and the exposed base. With n fins in an array, each of surface AF, right? Remember, AF is the surface area of the fin. The total surface area is following, right? So what is this A sub T thing? It's the area of the fins and the exposed base. So it's the number of fins times the heat transfer area associated with each individual fin plus the area of the base, right? So add all that up. Okay, the maximum possible heat transfer rate would result if the AT surface were maintained at T base, right? So the entire surface of this thing, the entire surface of this, the entire surface of this, all being maintained at AT base. Um, and with this condition, um, you get Q max, right? So that's what this essentially says is we're just taking the convective heat transfer coefficient multiplying by the entire total surface area of the fins and the base that they're attached to, and then multiplying that by the maximum temperature difference, assuming the fins stay at constant temperature all the way down their length. The book has a series of kind of intermediate steps, which I'm not going to show you. If you're interested, you can go and find them in the book. But the end result is that you get this equation for the fin efficiency, or I should say, the efficiency of an overall uh, array of fins, right? So 1 minus n times AF divided by AT multiplied by 1 minus the efficiency of a single fin, right? So this is an equation that you can use, or if you're interested in how it's derived, you can go to the book and see its complete derivation in the book. Okay, so just like with a single fin, we can use the heat rate to come up with an equivalent resistance, right? Because how useful, right, to have an equivalent resistance for an array of fins that I can then use all of my one-dimensional circuit stuff for to do simple calculations for temperatures and heat fluxes. So I say here, overall surface efficiency gives the total heat rate for the fin array. So here's the total heat rate. It's the fin efficiency times HAT, which combines with the 1D circuit analogy to create an equivalent fin array resistance. So I'm going to take that same idea that if I take the temperature difference from the base to the ambient and I take the total rate of heat transfer, which is this, take the ratio of those, the quotient becomes the resistance, right? Because that's the same form that we've always seen, right? That um, delta T over R equals Q. So this is just delta T over R equals Q, just rearranged to solve for R. This R is R sub T naught. So T is for thermal and naught is for just an array, right? So we use the same notation here, same notation here. That's what that little naught means. Right? Okay. And then here's the expression for that resistance, just one over huh. I'm gonna check on this. Let me check on this. This seems right because if I divide this by I'm gonna check on this. This is probably right. I copied it from the book, but something seems off to me. I don't there's no there's no theta b in here. So let me I'll come back to this. Okay. So R naught or R sub T naught is the effective resistance accounting for parallel heat flow paths by conduction and convection in the fins and convection from the prime surface, right? So what we're talking about is we have some heat transfer from this is the surface that I'm trying to cool that travels up the fin, right? So that is yeah, that's this resistance, right? So here's the temperature of the base. Here is the heat transfer resistance that's presented by all of the fins, right? So N times um, the fin resistance times H times AF, right? And then here is the heat transfer from this kind of intervening surface, right? So the surface that does not have the fin on it, right? And that's like basically everything else, right? The area that's not covered by the fin, that's AT minus NAF multiplied by the convective heat transfer, right? And these are resistances, so it's just one over that and one over that. That's where this exponent to the negative one comes from. So these things act like two resistances um, in parallel, right? Because one heat transfer path is this way, the other heat transfer path is that way, and they're both transferring heat into the ambient environment, right? Which is at T infinity, right? So that's why there are two resistances um, in parallel. And then I'm just going to use my nifty um, circuit analysis to put them together from two resistances in parallel to just a single combined unified resistance, right? So yeah, okay. So this is actually correct, right? Because I'm looking here. This is a figure right out of the book. I said I would come back to this, and here I am. Figure right out of the book, right? So this is it's one over um, efficiency times H times AT, right? One over efficiency. Yeah, okay. So this is right. Okay, sorry. I'm confusing myself for a little bit. I did a lot of copy pasting to make some of these equations, and I worried that I copy pasted something wrong. So this is right. Okay. Um, cool. So let's move on to okay. So now that I have an expression for the resistance presented, thermal resistance presented by an array of fins, I can start asking questions about like manufacturing techniques, right? So what happens if I have just a surface that I'm trying to cool and I want to put an extension on that surface, but the extension gets added to the surface after the manufacturing process is over, for example, by welding or brazing or press fitting. So I say here, if fins are machined, integral to the surface from which they are extended, no base contact resistance is there, right? So that's this situation where these fins are an integral part of the underlying metal, the underlying material. Um, Great for heat transfer, very hard to manufacture that, right? Very tough to run I'm not even sure how you would do this, right? You'd probably turn this thing on a lathe, and then you'd have some kind of anti-fin shaped cutting tool that you would stick in here to make these fins, right? So very difficult to do that. Far easier, and I say here commonly, fins are manufactured separately and attached to surfaces by a metallurgical joint. So when we were talking to Sandvik today, they actually mentioned this. So in their uh, finned tube heat exchangers, they start out with the tube, and then I think Atif said that he welds the fin, or the manufacturer of their oil cooler welds the fin in place. So there is actually a weld here to attach the fin to the underlying tube. So commonly fins are manufactured separately and attached to surfaces by some sort of metallurgical joint, adhesive joint, hopefully it's conductive, press fit, or threaded connection. We are in class in the lab actually going to explore the threaded connection, right? You guys are going to basically do a heat transfer experiment where you screw a threaded pin into a surface, and then you're going to measure rates of heat transfer by temperature from that surface, and you're going to have to contend with a threaded connection. And then we're going to squidge thermal paste into that connection and see if it changes the answer. So all of these different ways of connecting fins create a thermal contact resistance, R sub Tc, T for thermal and C for contact. RTC may adversely influence overall thermal performance, right? Because you're not introducing a resistance, right? We already said that these surfaces are very, very sensitive to putting fins on them. If the fin creates a bigger resistance to heat transfer than if the surface were just kept bare, that fin is not worth adding. And now we're adding an extra resistance to a spot that's already kind of sensitive to having a fin on it. So we have to be very concerned that the fin may adversely influence the overall thermal performance. So I've created here a representative effective circuit resistance with an embedded contact resistance, so you can see how you would actually perform this analysis, right? So here's the expression for contact resistance, right? It's just that same temperature difference over Q dot T, and this is 1 divided by, this is a fin efficiency for contact resistance times H times AT, all in the denominator. Okay, so what does this actually look like from a heat transfer perspective? Well, we still have our surface that we're trying to keep cool. We do have heat transfer away from the non-fin part of the surface, so that's this side of the thermal circuit. And then we have heat transfer through the fins, but the fins are now attached using, one of these techniques or maybe some other technique which presents a resistance to heat transfer. And so here is that resistance to heat transfer, and then here is the normal fin resistance, and those two act together as two resistors in series, which you know how to deal with from your circuits class. And then once you combine those, you can put them together as resistances in, then they become two resistances in parallel, and then you can combine them into a single equivalent resistance. The book goes through how this is derived. I won't bother with the derivation because you can look it up, but this is the expression for the efficiency of a pin of a fin where there's a contact resistance, and that contact resistance is known, so it gets plugged in here. And then you propagate that through and you find out what it is, right? So you want to obviously check to make sure that your efficiency is high enough to warrant the addition of a fin to the surface. Okay, so that's it for like the content that I wanted to cover. I do have 2 examples. So let's walk through these examples to kind of close this out. So example number 1 is we have a way of growing nanowires. So nanowires are grown by initially depositing a small liquid catalyst droplet onto a flat surface. The surface and catalyst are heated and simultaneously exposed to high temperature, low pressure gas that contains chemicals from which the nanowire forms. The catalytic liquid absorbs the chemicals through its top surface, converting them to a solid deposited onto the underlying liquid-solid interface, resulting in the growth of nanowires. The liquid catalyst remains suspended on the tip of the nanowire. Okay, so before I read the details, let me just go to the next slide and kind of show you what this is. So we have, right, this is like zoomed in, right? So we have some surface. We want to grow a very thin nanowire off of the surface. And so we put a liquid catalyst on the surface. The liquid catalyst absorbs gas from the surrounding environment. This gas is kept at, as we'll see, high temperature. So it absorbs gas from the environment. It basically self-assembles the molecules of that gas into this nanowire, and the nanowire starts to grow, right? But the catalyst, because it's a catalyst, right? You should remember from chemistry, catalysts don't actually change their chemistry. So whatever the catalyst is doing, it just keeps on doing it, still absorbing gas from the environment and converting it into nanowire. It just keeps on growing. So here, right, it just keeps on growing. And like I said in the beginning, everything is a fin, right? So this now, as this thing grows, starts to look like a fin protruding from a surface. And this is kind of a strange situation in that the surface itself is cold and the surrounding environment is hot, but the catalyst stops working, we'll see in a second, at a particular high temperature. So this nanowire can only grow so far. The tip keeps getting hotter and hotter and hotter, and eventually the tip reaches the temperature at which the catalyst stops working, and that's the maximum length of the nanowire, right? So here, consider growth of a 20 nanometer diameter silicon carbide nanowire from a silicon carbide surface. The surface is maintained at 2,400 Kelvin, and the liquid catalyst must be maintained somewhere between 2,400 Kelvin and 3,000 Kelvin in order for it to function. Determine the maximum length in nanometers of the nanowire that may be grown from for the conditions of forced convection coefficient H, 10 to the fifth watts per meter squared Kelvin, and TS. Oh, okay. S is for surrounding. Usually we use TS is 8,000. I think this is a typo. I think this should say um, T infinity is 8,000. So yeah, I'm pretty sure that's right. T infinity is 8,000. Not TS. I just copied this down to here and I forgot to change it. So T infinity, I'll change that on the final slides, equals 8,000. Assume nanowire properties are the same as bulk silicon carbide. For these temperature conditions, the K value for bulk silicon carbide is 30 watts per meter Kelvin. Okay, so we've already seen this graphical representation of what's happening, so I won't go through this again. But here are my assumptions. So one, the nanowire is a fin, right? Everything is a fin. All the fin assumptions are valid. So things like I'm in constant temperature across the width of the fin. Um, the properties are constant up and down the length of the fin, right? All those assumptions that were built into the original fin derivation are all valid here. Um, the nanowire growth rate is slow, and that slow is our hint that we are in a quasi-steady uh, equilibrium state, right? So quasi-steady state conditions. This growth happens fast enough. Sorry, this growth happens slow enough that we're not actually worried about the impact of the growth of the nanowire on the heat transfer, right? We're just basically taking a snapshot of this and assuming that the growth is slow enough that we don't have to worry about non-steady state conditions. The nanowire growth is going to stop when the tip reaches 3,000 Kelvin, right? Remember, it's in an environment where T infinity is 8,000 Kelvin, but it's anchored to a surface that's at 2,400 Kelvin. So this is going to act like a fin. It's going to get progressively hotter and hotter and hotter until it crosses that threshold of 3,000 Kelvin, and then it's going to stop growing. And then finally, we're going to ignore nanoscale heat effects, right? So we're not going to worry about, this thing is very, very tiny nanometers, right? So we're probably going to have some phonon effects here, some scattering effects. We're not going to worry about any of that. We're going to treat this like a bulk object that does not have any mean free path or phonon or any of those effects that we talked about in chapter 2. Okay, so my approach, of course, is to treat the nanowire as a fin with a prescribed tip temperature. That prescribed tip temperature, of course, increases as the fin grows, but we don't care what the tip temperature is until it gets to 3,000 Kelvin. That's the spot where the growth stops, which is what we actually care about. And so that's what we're going to prescribe as the temperature. And then we're going to solve for the L that this fin is able to achieve when that tip temperature is 3000 Kelvin. So in a way, this is very cool. I like this problem a lot. That's why I picked it, because we're basically solving the fin equations in reverse, right? Instead of solving for the tip temperature or a temperature in some spot in X for a particular set of boundary conditions, we're basically saying how tall does the fin get for a particular temperature condition instead of the other way around. Okay, so how do I tackle this? Well, I need the temperature field as a function of x for a fin, single fin that has a prescribed temperature, right? So this equation comes from, if I go all the way back to my table, too far, prescribed temperature, here is the temperature field for a prescribed temperature, right? So that's where this equation comes from. So let's move forward into the example again. There it is. Okay. So that's the equation. Um, I am going to figure out what M is um, and what H over MK is, because those show up quite a bit in this in this equation. So I'm going to figure out what those are. So M is just this combination of variables. So I'm going to plug in the values that I know. The perimeter has pi d in it. The cross-sectional area has pi over 4d squared in it. The d's cancel, the pi's cancel. That's how I get here. And now I plug in my known values, and I get 8.165 times 10 to the fifth meters to the minus 1. So that's my M value. And then now that I know M, I can figure out H over MK. So here I am plugging in all the known values for H and K. And here's the value for M that I just, oh, here's the M that I just found. And so I get 4.082 times 10 to the minus 3. And I need this ratio of temperatures, right? So this is the temperature difference between the tip of the fin and the ambient environment, and then the base of the fin, the ambient environment. And yes, I was right. The T infinity, the ambient environment, is in fact 8,000, right? So remember here, I said there was a typo. This should be T infinity. Yes, I've just confirmed that it should, in fact, be T infinity. And so that ratio of thetas is just 0.8923. And now I know everything I need to know, right? So I can take my ratio of thetas, plug it in over here, put in my values for x is L, right? So L minus L is 0. That's where this 0 comes from. L minus L is 0. That's where this 0 comes from. The numerator just becomes 1, right? Because hyperbolic cosine of 0 is 1. Hyperbolic sine of 0 is 0. So that's where this 1 comes from. And then I've got hyperbolic cosine of ML, which is just some number, plus H over MK times hyperbolic sine of ML, which is just some number. So I just plug in those numbers, and out pops a length of 589 nanometers. And I check this against the book, and I check this against AI, and yes, in fact, that's what it is. So with the exception of that one T infinity typo, this one is solved. Okay, let's do one more. And let me just say, the reason that it took me so long to make this lecture is because this is a really hard problem, and I did not know that when I picked it, and it took me like 2 days to solve it. So, so apologies that this lecture is a little bit late, but man, I worked real hard for you guys to get a solution to this that actually made sense. So, and this goes all the way back to, I remember I said I would talk about this here, right, where we said uh, thin, closely spaced fins are usually good, but not so close that they reduce the H value between the fins, right? So I wanted to give you an example of how that would actually impact the performance of the fins. And so that's where this problem comes from. But it is a doozy. Okay, so due to fluid blockage, the convection heat transfer coefficient for finned and prime surfaces. So prime surface is just the surface where there's no fin, right? Prime surface. Fin and prime surfaces of a fin array generally decreases as the number of fins increases, right? Just like I said, because they start interfering with each other's H. So we're going to consider the fin array shown, just simple rectangular fins with W, width of the fin, 22 millimeters, T, the thickness of the fin, 2.2 millimeters, and L, the length of the fin, also 22 millimeters. The fins are made of aluminum. I looked up the value of the thermal conductivity for aluminum at kind of the temperatures that we're talking about, which is this. And the base and environmental temperatures, there should be a parentheses here to close that. And the base and environmental temperatures are T base is equal to 368.15 Kelvin, and T infinity is equal to 293.15 Kelvin. Okay, so we got those two temperatures. Um, we're given that we can approximate the value of H as the maximum value of H, so like the free stream value of H, which by the way is 50, multiplied by 1 minus n over n max, where n max is the maximum number of fins that can be placed on the surface. And then we're given some physical parameters. N max is equal to 22 millimeters divided by 2.2 millimeters, which is 10. So the total number of fins that can be placed on the surface is 10. And again, H max is 50 watts per meter squared Kelvin. And so we're asked to, for that H value, to determine the total heat rate for one fin, two fins, three fins, four fins, and so forth, all the way up to nine fins. And then we're asked to determine what the optimal number of fins is. And as we'll see, as we add additional fins, the benefit of adding fins goes down from an overall heat transfer rate. And so there actually is an optimal number of fins, which is not nine, and it's also not one. So there's these competing effects of we're adding more cross-sectional area, or more surface area to allow for heat transfer, but we're also reducing the H value because the fins are getting closer and closer to each other and starting to feel each other's wakes and boundary layers. Okay, so this is, I think, an easier way to do it. For full disclosure, I tried to do it the way that the book wanted it done, so this is my last slide, and I did include that approach after the last slide as a series of backup slides. This is a disaster, right? It works, but man, this is really bad. I didn't do it this way. I tried it this way. I ended up using like fin efficiencies and AFs and ATs and ABs and array efficiencies, and this just got to be a real mess. So this is the way that the book did it. I don't like the way that the book did it. I did it a different way. I think my way makes a whole hell of a lot more sense. So, but if you're interested in the way that the book did it, those slides are there. You can go to those slides and you can check that out. I'm not going to go through that because it was a disaster. So the way that I did it, which I think is pretty clever, if I do say so myself, is just to recognize that the total heat transfer from the fins and the primary surface is just the number of fins times the heat transfer from each individual fin plus the heat transfer from the prime surface, right? So I'm basically treating each fin and the surface as just two resistances in parallel with each other, and just whoops, and just adding them up, right? So that's where this expression comes from. Um, we need this thing called a sub b. That's a sub base. So what is a sub base? That is just the width of the fin times the length of the base minus n times t, right? So what is that exactly? So here's t. So n times t is the number of fins multiplied by this little area. And then L sub B is the total length of the base, right? Which we're given, right? It's here. So all I'm doing is taking the length of the base, subtracting out the areas of each one of these little tips, which by the way, because these are rectangular fins, is also the area of the connection point here. And then just multiplying that by the width. And what that's giving me is effectively the area of the prime surface and not the area of the fins, right? So that's what this is. A sub B is the area of the base, basically the exposed surface that doesn't have fins on it, which we'll need later on, as you'll see. And then here is my heat transfer for adiabatic fins. Yeah. So why did I use this equation? Well, it goes back to my assumptions. So I'm going to imagine or assume that we are in steady state. All my fin assumptions are valid, right? So my temperatures are constant across the width of the fins. Material properties don't change with dimension or direction, right? All those fin assumptions. We're going to neglect radiation because we do have this exposed tip. And I'm claiming that it's adiabatic, so I cannot have any radiation off of that tip or off of any of the other surfaces. That complicates things. Um, we're going to say that H is uniform despite the presence of the fins, right? So I'm going to get a reduced value of H per this equation. But once I have that value, I'm going to assume that it's the same across this surface, the tips. It's basically the same everywhere, right? Probably not true in the real world, right? Because these things are going to form boundary layers and the boundary layers are going to combine and they're going to slow the flow down. But I'm going to assume that once you calculate the H value, that it's uniform despite the presence of the fins. And then I'm gonna treat the tips of the fins as adiabatic because that's just the easiest boundary condition, right? So that's just my assumption to make my life easy, right? And the fin tips are relatively small compared to the other area, so that's probably a good assumption, at least for an approximation. Okay, so I've already talked through what these equations are. I kind of did that out of order. Sorry about that. Um, so we're going to now calculate the parameters that we need to solve for a single fin. So the perimeter of one of these fins is just um, W plus T times 2, right? So W is the width, T is the thickness, and the perimeter is just me kind of wrapping around the outside of this thing. And so that's where this comes from. So it's 0.0484. Um, A sub C is the width times the thickness. So let's look at that. The width times the thickness. Okay. That's the cross-sectional area of each individual base or each individual tip. So I think, yeah, A sub C. Yeah, okay, right. Cross-sectional area. Okay, that makes sense. So that's lots of 484s here. 0.444, 0.00484. Okay. Knowing P and AC, I can calculate M, lowercase m. Notice H, I'm leaving that as a function of N, the number of fins. Everything else is just a number, right? So K is a number, P is a number, AC is a number. So what I get out of that is 14.494 multiplied by the square root of 1 minus n over 10, right? So I'm leaving this in terms of n because remember, what I want to do eventually is to have an equation where I can plug in n equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I made that easy for myself by just leaving everything in terms of n. Um, Okay, M, capital M, same story, right? It's just combinations of numbers that I know. So I'm going to plug all those numbers in, but notice I'm going to leave H in terms of N so that later on I could just plug in an N value and I don't have to go back and solve this over and over and over again. Okay, so now I've got my M value. So here it is in terms of N. Um, and I can plug in my Q sub F. So this is Q for a single fin. And notice again, I know capital M, I know lowercase m. This is the equation for heat flux from a single fin with an adiabatic tip, which I now have in terms of n, the number of fins, right? Because even though this is for a single fin, um, if I increase n, that changes H, and that reduces the heat transfer from a single fin, right? So it is, even though I've just got a single fin, it is still a function of n. And then here is my area base area. So I'm just plugging in the numbers there. And again, I get a value which is a function of n, so that I can plug in n and come up with the base area, which of course will change as I increase the number of fins. And now I've got everything I need to plug into my equation. N times QF plus H times AB times theta B. And so now I just plug in what I know into this equation. So here it is. It took me 3 lines to write it in its full numerical form, but here it is. Notice that everything is a function of n. So now what I can do is just plug in n equals 0, n equals 1, n equals 2, and so forth. And I get different h values. So notice that h is going down as the number of fins is going up because the fins are becoming more and more and more crowded, right? So they're forced convection is going down because they're sitting in each other's wakes and sitting in each other's boundary layers. And then look at this. How cool is this? So the thermal heat transfer from the surface for no fins is 1.8. If I add a single fin, it goes up to 5. Two fins is 7.7. Three fins is 9.8. Four fins is 11.4, and so forth. And then I finally here at 6 fins reach a point of diminishing returns, right? Why? Because even though the surface area that I'm doing heat transfer from is going up, the convective heat transfer coefficient is going down. So at 6 fins, I reach diminishing returns. At 7 fins, my total heat rate is lower. At 8 fins, it's even lower. At 9, it's lower. So the answer to the original question, how many fins is the optimum number, is 6. And the rate of heat transfer that I get for 6 fins is 12.675 watts. And just note, right, I cannot have a fractional number of fins. I cannot have 5.5 fins or 6.6 fins. There might be, maybe a little more optimization here if I was allowed to not use a whole number, but fins come in whole numbers, right? So I have to use a whole number. Okay. So that's the result, and I actually checked this against the answer given in the book and the answer that AI gave me for the same problem, and it agreed. So this is a check. I got this right. Good for me. And that's the end of the second example. But wow, this one was brutal. Especially like I said, I spent like a day going through the solution the way that the book wanted it, and wow, what a mess. So my way I think is a bit more simple, but it gives the same answer. So probably better in that regard. Okay, so that brings us to the end of this lecture. Thank you again, as always, for your time and attention. I know that these things are really long, but I just like to cover stuff that's all the same, all in just one big long lecture instead of trying to break it up into these kind of shorter 15-minute segments so that you guys are just seeing all of the content from a section or a chapter of the book all in just one sitting. So appreciate your time and attention. We will wrap it up there, and I will see you guys later. Thanks. Bye.